Good morning. Do you have a PowerPoint or speech? Okay. Good morning, everybody. Minasan, ohayo gozaimasu. Distinguished guests, ladies and gentlemen, it gives me a great pleasure to welcome all of you to the 9th UNISEC-Global meeting and 8th Mission Idea Contest, which held with the cooperation of Nihon Pashi Space Week. This year marks the 10th anniversary of UNISEC-Global. This event is a culmination of an enormous collective effort which began in 2013 when the UNISEC-Global was launched. Inspired by the achievement of UNISEC Japan, UNISEC-Global was established with a vision: by the end of 2030, let's create a world where university students can participate in practical space projects in all countries. The journey of UNISEC-Global was started and will keep going with the contribution from many esteemed professors, students, and administrative staff from all over the world. Mrs. Rei Kawashima, Secretary General of UNISEC-Global, will give a welcome speech about what was achieved in the first decade of UNISEC-Global. Please welcome to the platform Mrs. Rei Kawashima, the Secretary General of UNISEC-Global.
Thank you very much for your kind introduction. Good morning, everybody. So, okay. Good morning. One more. Good morning. Good. All right. So now you woke up. Okay. All right. So today, this is the third day of this week, and Wednesday is a quite tough day. But let's begin with full of energy. Okay. So, what are we doing now? Yeah, we are making history now. Let me introduce what happened. By the way, how many people are younger than 25 years old? Okay. Yes, yeah. Professor Nakasuka is also younger than 25 years old. Okay, that's fine. Okay, so 25 years old, 25 years ago, nobody believed that university students can make satellite and launch it, operate it. Nobody believes that. And 10 years ago, when we started UNISEC-Global, very few people believed the students from non-spacefaring countries can build and launch and operate satellites. But now, in 2023, everybody knows, of course, university students can build satellites. Even the country is not a spacefaring country. No, even if the government doesn't have satellite, university students can build, launch, and operate satellite. Everybody knows that. So what happened? Somebody started the activities. And then let's imagine what will happen 10 years later, 20 years later. Okay, 10 years later's reality we are making now. So each of you is contributing to making the history. Is it fun? Okay, so the futures are in our hands. Whatever happened, don't be discouraged. We can keep on going. So let me talk about UNISEC history very quickly. We started these activities in 1998. Thanks to Professor Twiggs. Actually, we have Professor Twiggs' very interesting, inspiring, very shocking video later. And also Aeropac, which is the American amateur rocket group. And they supported the first CanSat launch in Nevada. And today we invited Professor Nakasuka and Professor Tsuda to make a presentation about their history. Their history is exactly the same as UNISEC history. So CubeSat started 1999. Some of you are not born yet. Really? Okay. But now we are UNISEC-Global community spread it in the 65 regions, and the 24 local chapters are already established. And we have more than 200 universities members are working on satellite or rocket or the ground station or data analysis or whatever. And now we are here for the 9th UNISEC-Global meeting in person. So yesterday and the day before yesterday, we organized Heptasat training and space job fair here. And today is November 29th, and we will have a very nice keynote speech. And in the afternoon, mission area contest will be held. And in the evening, we'll have a reception. We'll have a reception. By the way, you guys will have a very nice lunch here. And reviewers need to have a meeting. Some of them will meet for the first time. So we need to launch a meeting to set up everything for the missionary contest. So please stay here. And the missionary contest will be held in a different building. And our staff will take you to the building. Don't worry. It's just 5 minutes walking. Okay, and tomorrow we'll have a regional report from each point of contact and the Earth observation data workshop, which will be held by the Aerospace and Restec. They came here and to give you a very short but very meaningful data analysis hands-on training. And in the evening, tomorrow, student session will be held. It will be very, very interesting, and only students. Only students, please. And in the last day, we'll have a panel discussion on the constellation mission. We want to launch UNISEC constellation mission in the future. So we'll have a panel discussion there. And in the afternoon, we'll have JCube workshop. If you want to have a very low-cost launch opportunities, please join this, because there is an opportunity to get a very low cost, very low, which means one third of the normal price. So you should attend if you want. And we have some proposal of new initiatives from younger generations. And in the evening, gala dinner, we will go to the Yakatabune, which is a Japanese boat trip, and we will enjoy dinner on the boat. And I think many of you, the missionary contest finalists, will be invited, and I'm very happy to able to invite you. Okay, so now we have sorry, okay. So I also have an announcement. We'll start UNISEC-Global activities again. UNISEC-Global is UNISEC student organization global, okay? And then you will find it on the Thursday evening. Okay, so let me conclude my presentation. The first decade of UNISEC-Global, we focus on low Earth orbit. And from now, of course, we want to try to reach to low Earth orbit, but we want to go to the moon and beyond. Let me conclude by quoting the African proverb. If you want to go faster, go alone. If you want to go farther, go together. No, space is infinite. We can go further and further to the deep space and maybe out of the solar system if we decide go together. Thank you very much. Enjoy your workshop.
Thank you, Mrs. Rei Kawashima. In November 1999, during the Japan-US Science, Technology, and Space Application program, Professor Robert Twiggs proposed CubeSat as an educational satellite that can be built by university students. So we will watch together about 15 minutes video about CubeSat educational experience from Professor Robert Twiggs.
Hi, I'm glad to have the opportunity to do this presentation at the UNISEC meeting, and appreciate all of you. And let me get started here. Okay, what I wanted to do is to talk about a little bit about CubeSats for education. I'm sure all of you know that the main reason that the CubeSat came about was for education of university students. They were all very excited about wanting to build something, so let's take a look at it. But note, I put here not anymore, so there's a problem with it. I would like to show you and see if there isn't something that we can do about it. So a little bit of introduction. I know a lot of you, but I was involved with introduction of the CanSat, the CubeSat, and the Pocket Cube for educational applications in space. A little bit about my career. I started in the academic side in 1982, and from then until 1984, I was at Weber State University in Utah. Started the Center for Aerospace Technology there, and while I was there, with the help of students and mentors, we built and launched 2 educational spacecraft. I went to Stanford in 1994, was there until 2009. When I was there, I started the Space System Development Laboratory, and that's where I introduced the CanSat and the CubeSat. From 2009 to 2019, I was at Morehead State University And while I was there, we launched the first CubeSats. So the NewSat was actually launched. NewSat 1 was launched in 1986 with from Weber State University group. And here are the faculty and mentors to build this satellite that was launched off of the gas can. And it was made by a group of engineers that actually had never built a spacecraft before. If we'd known, we'd probably not. We would probably turn the project down. But it was really good for the students and the learning prospects of the faculty and mentors. So when I moved to Stanford, after 4 years at Stanford, we needed a new standard for student-built satellites. We built 2 of these microsatellites, and it took quite a while to get them done, and it's very difficult to find a launch for them. The thing that I found out is the satellite itself was really too big, took too long to build for when specifically it was in a master's degree program. Too much room for new ideas, difficult and expensive to launch. And then looking for a new standard, we wanted to reduce the size and see if we could find another opportunity to launch them. So the goals were small size for limited room, low cost to launch, and see if we could develop a container that we could have multiple satellites in. And it was safely enclosed and protected the primary satellite on a rocket. So the new standard, we eventually come to call it a CubeSat. It started out as a 4-inch Beanie Baby box, and it was only that size because I was looking for something that would match the solar cells that I had. So it was like a jack in the box. We could put 3 units in the launcher. The launcher eventually became called the P-Pod for Polypicosat Orbiting Deployer. And that was co-developed alongside with Professor Jordi Bussari at Cal Poly. And we first shared this concept in the JAXA conference in November of 1999. Now, when people first looked at it, they didn't like the idea. They had some interesting comments. They said it's the dumbest idea I've ever heard, too small to do anything useful, and you academic guys aren't smart enough to build these satellites. But we had one group that liked it, and it was the Japanese. When we showed the concept to them, they liked the idea. So a little bit about the CubeSat timeline. First launch was in 2003, and you can see all of the satellites that were launched there on that first launch. It was actually, we went through the University of Toronto and did this on a Russian converted ICBM. We had an additional launch in 2005, and then a launch first from Japan in 2006. In 2004, there was a NEPR with 14 CubeSats on that didn't make it into orbit, and you can see a hole with 14 rapid assembly CubeSats on there. But you know, it was exciting enough that it still began. So eventually it was accepted by most of the universities, the amateur radio group, commercial aerospace, and finally the government. So we're working right now, Aaron Zuckerman and I are working on getting the CubeSat history. So we're writing a history of how the CubeSat was made and adopted. And we're looking for more Japanese and international participants to tell their side of the story and how the CubeSats has affected their country. So if you're interested in this, and I know some of you have already talked to Aaron, please get a hold of him. You can see his email here, or you can scan the QR code. So what has been the value of CubeSats? They were really accepted by the students in their projects. It really produced new space industry leaders. A lot of these students have been involved in it are now leaders in the space industry. It changed the interesting concept about how to build satellites. It's not near as cumbersome as previously with NASA supervising it. The use of ride shares to reduce costs went from large to small, less expensive missions, and reduced the development time on it. Some bad things about being popular: licensing becomes more difficult once the government gets in there. Cost of launching tripled. Expectations and complexity of the missions increased. It's generally on the students. You have a faculty advisor or mentors, but sometimes they get into the project too much and make it so difficult that they think they're going to win a Nobel Prize from it. The time it took to develop, leave out the initial students, because it takes anywhere from 3 to 5 years, and sometimes it never gets launched. Students are not learning management standards. What we needed was, and what we wanted was this sort of thing: the open access to the students. And this is what it became. It became much more complex. The government got a hold of it, and the commercial industry got a hold of it. Costs went way up, and complexity went way up. So, but what about the future? Are CubeSats still meeting the original needs of the students? Are they simple to build, inexpensive to launch, minimum paperwork, less government regulations? Well, if we go way back, we go back to the Sputnik, a very simple satellite, rather large, but a simple satellite, and what it did. Also, if you look back at the first ones that the U.S. come up with, was the Vanguard satellite, and Vanguard 1 didn't get launched. The rocket blew up. It got dumped out on the ground, and that's, by the way, that's the Air and Space Museum in Washington, D.C. to look at. Vanguard 2, a little bigger, but got launched and worked. And so what is needed for a first-time student mission? It's really a mission starting with some mission management concepts, showing them, how to plan what they're going to do, set up timelines, and so on, and have some firm development goals. Don't change the development goals if they're rather simple. Don't change them as you go along. It must be completed and launched within 2 years. We'd like to see it no more complex than the Sputnik. And we would like to have an orbit life of 6 months or less, so there's no debris associated with it. So here's a challenge to you. How about something like the Vanguard, or something like this little ThinSat here? So we're going to get the academic community back to the basics for first-time CubeSat students, and maximize the opportunity of a single launch, make the design low cost, and use simple sensors for a low downlink data rate. Make it simple. The SlimSat concept is shown here. We'd like to make the satellite like what is the cross section of a CubeSat, and here's a concept that Nick Pugh in Louisiana has, that is a real basis for what we could do. Is the breakout model here. Fly it on balloons. You have the receiver station here, and everything is working good. You can put for up to 21 missions per deployer for a 3U. evolution of the thin-sat concept, seven of these little picosats per 1U, and affordable for even pre-university students. So the question is, to learn more about the SlimSat, you can reach out to either to myself or you can, and if you want to contribute to the CubeSat History Project, get a hold of Aaron Zuckerman at this email or scan this code. Any questions? Thank you. Appreciate your time.
And let's move to our first keynote speech. UNISEC-Global was inspired by the achievement of UNISEC Japan. Professor Shinichi Nakasuka, professor of astronautics at the University of Tokyo, and one of the co-founder of UNISEC Japan, Professor Nakasuka will tell us how Japanese micro nano-satellite activities started and its outcome. Please welcome to the platform Professor Shinichi Nakasuka.
Good morning, ladies and gentlemen. Thank you very much for coming to the UNISEC-Global meeting. And I'm very happy to make our first keynote speech about our activities. And in my title, it looks like this: History of University Challenge towards satellite, smaller satellite, how Japanese micro nano satellite activities started and its outcomes. What? 画像本当だ。ちょっと待って、just wait a moment. Okay. Okay, so first I'd like to show the University of Tokyo's activity. So we developed and launched the world first CubeSat in 2003. That was the 1 kilogram satellite called the Psi-4. And around that time, we developed and launched this kind of the experimental or educational satellites. And then we challenged the space science together with National Astronomical Observatory of Japan in the name of the Nano Jasmine. That is a very high-level space science satellite. And then we started the Hodoyoshi project funded by the government. And we developed and launched the 3 Earth observation satellites, Hodoyoshi 1, 3, 4. And recently, we developed the Strix Alpha, which is a SAR, synthetic aperture radar satellite, together with a venture company, Synspective. And many universities, many countries around that time asked us to teach them how to develop a satellite. And we collaboratively developed the one satellite together with Vietnam, Micro Dragon, and the Rwanda, RuaSat-1. These satellites were launched by Japanese Epsilon rocket in 2019. And also we did several technological demonstration or entertainment satellite. And recently we are focusing on the deep space exploration satellite. And we launched the world first 50 kilogram class deep space probe called the Procyon in 2014. And then last year we launched the Aquarius, which is just a 6U CubeSat, which is going toward the moon. And then recently we launched the 6U CubeSat together in collaboration with Sony company. And in total, our laboratory developed the 15 satellite, and the more than 120 students were trained in this kind of the practical project. And now they are working very actively outside of the university or inside of the universities. And starting from this kind of the activities of Japanese universities, so in the UNISEC framework, more than 60 university satellites were developed and launched into the space. And from CanSat to CubeSat and more sophisticated satellite have been developed, and they are contributing to the national space activities and creating several venture companies. So this is an overall view of the Japanese current status. And let me first show how this kind of activity started at around the 1990s. So the Professor Twiggs already mentioned about a birth of the CubeSat concept in 1999. So around the 1990s, universities of the European countries or the American countries already developed the university satellite at that time. But in Japan, there is no such kind of the concept. And that means that we are very much behind them. So in order to catch them up, I started together with several other professors, like a satellite design contest. This is very, very important. Through this, design contest, we could learn how to, conceptualize a mission and how to make the mission concept into the satellite design. That kind of the thing has been trained. And so this is very similar to the mission idea contest, okay? And but this is just a paperwork. But we want to do some more practical project. So we started the USSS, University Space Systems Symposium, together with the United States, universities. Universities from United States and Japan get together in Hawaii and create a certain mission, actual mission, practical project. And 1 year, we should continue this activity. And then the next year's USSS, we should report the 1 year result. So this is the framework of the USSS. Within this USSS, the concept of the CanSat appeared in the 1998 from Professor Twiggs. And then several universities participated in the CanSat, actual practical space project. And then the CubeSat concept was proposed by Professor Twiggs in 1999. And several universities in Japan participated in the CubeSat. And around that time, the UNISEC was created. Okay? And then the first CubeSat launched by two universities, University of Tokyo, our university, and the Tokyo Institute of Technology. So now we could catch the European or American countries, American universities. So this is what happened in the initial phase of the Japanese space development, universities space development activities. And now, after this, various projects by many universities and the startup companies are going on. So many universities are collaborating with the startup company to create a more sophisticated or more business-like satellite. So, but all of this kind of the activities was starting from this kind of the CanSat, CubeSat, and so on. And UNISEC has been a lot of contribution to this kind of the activities of Japanese universities. And the Professor Twiggs mentioned that the CanSat concept was born at the USSS 1998. And he suddenly stood up with a Coke can in his hand. And he told, let's make a satellite out of this Coke can. So that is the starting time of the CanSat concept. And initially, we plan to do like this. So each university will develop the one CanSat and launch it all together into the space. And we can operate these CanSat in the next USSS. So that is a very, very challenging concept. It was very difficult to find the launch opportunity at the time. So we switched to the suborbital launch experiment. So every year, so the students bring their CanSat to the United States in the Nevada desert, where the amateur rocket group called the Aerospace can lift our CanSat up to the altitude of the 3.6 kilometer. And during the descent, which will take about 15 minutes to 20 minutes, we can do a lot of experiments, just like using a satellite. So that is a concept of the CanSat. It's very similar to the satellite development and operation activity. So it gives us a lot of training, how to develop a miniature satellite system and how to make a project management or systems engineering. That is what we learned in the CanSat. And since then, many universities have been participating in the CanSat, and every year the students have been developing this kind of the very small 350 milliliter CanSat satellite or a little larger satellite, which can be launched by this Aerospace rocket. And this event is called ALICE, a rocket launch for international student satellite, which started in 1999. And then, as you see, that as time goes by, more and more universities from Japan or other countries participating in this ALICE. And unfortunately, we could not make it happen in the 2020 and the 21 because of the COVID problem. But now we have the 23rd ALICE in this year. It's good that now it's very easy to count. 2023, we can 23rd, okay? Because of the COVID, thanks to the COVID. Okay, so anyway, so then we went into the space. So CanSat is very good, but it did not go into the space. So we started the CubeSat program, a CubeSat project around 2000. And after 3 years, 2003, we launched the world first CubeSat together with the Tokyo Institute of Technology. And the cost is very low. We developed one satellite with just $30K US dollars. It's very cheap. And we bought almost all the parts from the commercial on the ground shop. And there is Akihabara, which is an electronic town near here. And we went there to buy the parts and to find out which is working in space. Okay, we should check the space environment, and we could find out this part is can work in space and so on. So in this way, we developed the satellite with very, very low cost, and the development time was just within 2 years. And we expected to survive in space for about maybe half year, but fortunately, it has been surviving space for more than 20 years. It is perfectly working still now. And not only the satellite development, but through this development process, we could obtain the ground operation, frequency acquisition, launch opportunity search by ourselves. Now that means we could make a way to the space at the time. Okay, so that happened in 2003. And at the time of the launch, okay, so this is a satellite. There is no port. Pod or something like that. So we should develop the launch pod by ourselves. And this launch pod was developed by the Professor Funase, who is now the associate professor in my laboratory. And then one guy is staying in the Russia to send some message to us. And so this guy is in Aerospace CEO, Dr. Nakamura. Okay, and many students are waiting for the signal to come. It's a very, very nervous and a very exciting moment. We are waiting whether our satellite can send the data to us and so on. So we are very much nervous about that. And we should wait for about five hours. Okay, the launch is taking place at 23 o'clock in the evening, and the signal is to come at around 4 o'clock in the morning. So we should wait for about 5 hours. And then on the next day, so that is the first voice from our satellite. So all the students are very much excited. And some students even have tears and so on. It was a very, very special moment for us. We never imagined that this small satellite can go to the space and do actual work in space. So that is a very, very special moment. So I'd like to encourage all of you to experience a similar type of the experience. So it was a very special moment. Okay, and so this satellite project manager was Professor Tsuda. And he will make a presentation later. So he has been working very hard. We'll never go home. Stay in the university and using the shower in our building and so on. So in this way, the students who are working very, very hard, okay, can realize this kind of the satellite project. And now, after the graduation, they are working in the every part of the Japanese space development activities very well. So in this way, the student time, training is very important. So I realize that. And so let me show some key strategy to launch the world first CubeSat. Why we can, develop and launch the world first CubeSat. So the no components are on website for the development of the CubeSat. There is now you can buy the CubeSat components very easily from the website, but at the time there is no components. So we should develop everything by ourselves. That gave us a lot of very good or very deep experience and skills and know-how to develop such kind of the component for the small satellite. And no ground test facility in our university. So we bring our, CubeSat in a suitcase to go to the other, facility, like a JAXA, NASA's facility or some company's facility and so on. And we have only little money. So as I said, the satellite development is just made within the 30K US dollars. And the key strategy employed in our first CubeSat looks like this. We found out and pursued what we can do within our limited resources. That means we did not aim at the high level. Only survival in space would be the main concern for us. And find outside supporters like technically part donators and so on. And implement survivability as much as possible. That is very, very important. And every time we kept this in mind, that is keep it simply as stupidly. So that is very, very important concept. We started from a very, very, very simple CubeSat. And after the success of this, we can go up to this next step. Okay, so that is a very, very important starting time concept. Now, let me show how we can make a survivability, implement a survivability into the satellite. So this is a inside structure of our first CubeSat. And the satellite's key system technology looks like this. It is non-repairable system. That means if it is, after it goes into the space, we cannot touch it. We cannot repair it, even if it fails. So we should implement the survivability as much as possible inside of the structure. And maybe you can see that the OBC system, TX, transmitter system, and the CW, RX, that is a receiver, and the CW beacon transmitting system. Each system has its own CPU, which is made out of the PIC processor. And these processors are working for their own subsystem. And in addition to that, they are watching the behavior of other subsystems. If that system has some failure, like hang up and so on, it reset the power line of that system. Then the system will go back to the normal state. Even in the one new CubeSat, we can implement this kind of the mutual monitoring system that works perfectly. Then after the 20 years, it's still working very well. So in this way, we should make the satellite die hard, okay? Mutual monitoring or reset operation, and the solar power generation possible in any altitude. So that is very important. If you have a large solar cell panels, then if the altitude control is very good, then the sunlight is coming to the surface of this solar panel. But altitude control does not go well. Then sometimes it cannot get solar power. But if you put the solar cell on all the surface of the body of the satellite, then regardless of the altitude, it can generate the solar power. That is a concept. And the under voltage control and the appropriate definition of safe mode, we could obtain this kind of the survivability concept or technology through our project. So this is very, very important system level technology for the satellite. And after the launch of our first CubeSat, we could obtain this kind of very beautiful picture of the Earth. Maybe more than 500 pictures were taken and downlinked to the ground. And at the first, so every year, so we could obtain many pictures, but we picked up one picture from each year. So maybe, as you can see, that the color has been changed from blue to yellow. The first time I saw this, I was very much scared that the color of the Earth has been changed from blue to green, yellow. But it does not screw, of course. It is because of the degradation of the lens material of the camera. It is made out of the plastic, plastic. So he is also the manager of this, camera mission. And so in this way, if your satellite survive in space for a long time, maybe you can get some, knowledge about the effect of the environment of the space. So that is happened in our satellite. And starting from this one CubeSat success, in the world, there is a very big game change towards a miniature satellite from a big to small, small number to large number. This kind of the change has been occurring all over the world. And not only the education, but also the remote sensing, telescope, bioengineering, and re-entry experiment, and communication, space science and exploration. Even the JPL, NASA JPL is trying to launch the series of the 6U CubeSat into the deep space like Mars and so on. And also the high resolution Earth observation satellite has appearing. And active players has been university and the venture companies, but now many countries think that this area is very important, and they started very large investment to this field, like the United States, Canada, European Space Agency, and China, and so on. And Japan was a little behind of such kind of the movement, but now, since maybe 2 years ago, they started the investment into this field. So now we can get some money for the development of this technology. And in 2010, we started the Hodoyoshi project. It is a governmentally funded project, and I was a leader. And together with about 12 universities and more than 170 small industry in Japan to create this kind of the world. We want to develop a paradigm of the 50 kilograms class satellite and its application. And we developed the Hodoyoshi 1, 2, 3, 4. And not only that, we developed the miniature advanced components which are suitable for 50 kilogram class satellite. And we created several missions, and also we established a ground station or ground testing facility infrastructure. And the Hodoyoshi is a very important concept, which is something like this: just good or good enough. That is not too much. Okay. For example, at the time, the JAXA or big company are developing a very high sophisticated satellite. It is, from our sense, it is a little too much. Okay. And because of that, such kind of the complexity, its cost is very high. Okay. And the development time is very long. So that is not good for the education or not good for the business and so on. So we should make a very good concept about something like a not too much satellite. So this is a concept of the Hodoyoshi, and we develop our satellite based on this concept. And let me show the several outcomes of the project. And this is a Hodoyoshi 3 and 4, which were developed within our building. And it's about a 60 kilogram satellite. And the cost is like this. We set a cost limit at $3 million US, and development time is 2 years is a limitation. And we achieved the development within this limitation. And the attitude control capability and the downlink and the power provision capability is very suitable for the space science as well as the Earth observation. So I think it was a very good cost of performance, high cost of performance satellite at that time. And let me show the several pictures taken by the satellite. This is a lowest resolution pictures camera, and the 240 meter GSD camera. I'm not sure where it is. And so the highest resolution camera at the time was a 6 meter. Now we have the technology of the 1 or 2 meter resolution, but at the time the 6 meter was a maximum. And maybe you can see the agriculture field one by one. So if you continually using satellite to monitor the agriculture field every day, maybe you can get some information about the diseases or lack of water information, and also you can predict the crop amount of the crop. Or during the mountainside, maybe the satellite can detect some landslide or other disaster and so on. So important thing is that this kind of the small satellite should not be launched. It is not good that this kind of the small satellite is launched only one. So if you launch many satellites, you can monitor this area every day or more than that. So that kind of the frequent observation is very important. And the small satellite is very suitable, such kind of the frequent observation, and it is a concept of the small satellite constellation. So now the many companies are doing this kind of the small satellite constellation for business. Okay, and based on the outcome of this Hodoyoshi project, we developed the 50-kilogram class deep space probe called the Procyon. Within just 14 months. It's a very, very short development period. And so it was launched together with Hayabusa 2, the Professor Tsuda's mission. And so Procyon looks like this. Okay, and it succeeded in the various experiments in the deep space, like a communication or navigation, guidance, and control in the deep space. And in addition to that, we could obtain several scientific observation results, like hydrogen emission from the Earth or other comets and so on. It was very good, successful mission. And based on the success, the students have been developing the 6U CubeSat called the Aquarius, which is planned to be going to the Earth-Moon Lagrange point 2. So NASA is very generous. They are offering the launch opportunity of the total 13 6U CubeSat, okay, on board of the Artemis 1 rocket. And so the inside of the satellite looks like this. It was very much packed inside of this. So Japan is very good at doing this kind of very packed thing. Do you know why? This is because we are living in a small house. Okay, so we are very good, very accustomed to such kind of way of thinking, how to make it small. Okay, so this is the inside of the satellite. So this is a 6U, that means a 10 centimeter, 20 centimeter, 30 centimeter. And we could develop several new technology like a red part, deep space transponder or registojet, water registojet thrusters. And so we have been waiting for the launch for several years, but finally it was launched by the American Artemis 1 in the last November, and now it is going to the moon. And the amount of the fuel is very much limited, so we should make this kind of the very complicated trajectory using many swing-by from the Earth or moon. And going toward the moon, Earth-Moon Lagrange point 2. At the time when our satellite flies very near to the moon, it could take this kind of the lunar surface picture. So it was very good. So this is Aquarius program. And also we have been working together with the foreign country to create or develop one satellite. This is Vietnam, called the Micro Dragon. We accepted total 36 young engineers from National Space, something like a Vietnamese Space Agency. And we taught them in the master course of the 5 universities. And together, we developed the one satellite called the Micro Dragon, and which was launched by the Japanese Epsilon rocket in 2019, and it works well. And this is another collaboration with a foreign country, together with Rwanda. And we created this one 3U CubeSat called the RuaSat-1, and launched by the Japanese H-2B rocket to the ISS and deployed from ISS in 2019. So in this way, we have been working together with a foreign country as well. And recently, so we are developing the Sphere 1I together with Sony. So the Sony wants a customer to operate satellite directly to capture various images like Earth someplace or moon and a star and so on. So it's a kind of entertainment type of the project, and we have been developing this for about 2.5 years. And this, January, it was launched. And maybe you can see the very beautiful pictures has been taken by this satellite. So this is because not only our satellite bus system is good, but also the Sony's camera is very good. As you know, that the Sony has produced a very good cameras, and also we can obtain this kind of the moving image of the Earth. It's very, very beautiful. And also we have been developing together with Taiwan Space Agency called the TASA to develop this one 6U CubeSat called the OnDaiSat, and which has a very high level Earth observation capability using TDI, time-delayed integration technique, to obtain 2.6 meter ground resolution. Okay, and we plan to launch this in the next year. And now we are at the final phase of the development. Okay, and what's the next? So we are now targeting to do this kind of the project, which is called the formation flying. We will not use a satellite only in one, but we put several satellites in the vicinity. And then this satellite will do some collaborative observation of the target stars and so on. Then we can obtain the more higher resolution. That is the concept of the formation flying. And up to now, the formation flying concept appeared, but its accuracy of the control of the relative position of the satellite is not so high, like a centimeter to meter level. But if we can improve that to the millimeter or micrometer accuracy, then we can make a higher level space science using the formation flying. So this is a concept, and we are studying about this. And the one example of the application is a synthetic aperture telescope. So these 6 satellites is, located in the geosynchronous orbit. And the light coming from the Earth will be reflected by these 6 satellites and converge to one satellite. And then we can make a, interferometric observation to, obtain the very high resolution pictures. Okay, so this is the concept of the formation flying synthetic aperture radar satellite. Another application of the formation flying is this kind of the infrared science. And we are now preparing to the development of the satellite called the Sirius, which has 3 satellites, 1 mother satellite and 2 daughter satellites. And the light coming from some stars is, first reflected by this daughter satellite and converged to the mother satellite. Then we can make interferometric observation. And then even the satellite is small, we can make a high resolution. We can obtain the high resolution pictures like the right figures. So this is a very, very new concept. It's very difficult because we should keep the relative position of the satellite with accuracy of the micrometer or millimeter. But now we are gradually getting the feeling that we can do that using the ground experiment as well as the simulation. So the next phase is really a demonstration in space. We are now planning to do that. Okay, and this kind of the high level satellite, but also this kind of the satellite has a educational significance still. And because it can provide a student with a practical training of whole cycle of space project, including the mission conceptualization, satellite design, modification, and launch operation. So that whole cycle of this, activities can be trained for the student. And important for the engineering education that because the student can get a feedback from the real world. And it is also very good for the education of the project management. Please guess what is the 4 important management tasks. You see, the first one is time, schedule. You should keep the schedule and also the budget and human resource. And what is the fourth one? So that is the risk. We should manage the risk. So this is a very important, for management task. So this kind of the management task can be trained by for the student by this kind of practical project. Not only the class lecture, but also this kind of the project is a very good training material for the student to learn this kind of the management task. And through our experience, I can say that the effects were found more than expected, and it also contributed to other technological areas. Okay, so this CanSat is a very good educational material. So if you don't do the CanSat, please start an experiment, and we can train the student in various fields using the CanSat. So even if you're not going to the United States to participate in the ARES, but also in your country, you can do this CanSat. Drop from a high tower or using the balloon or using a drone, you can lift your CanSat up to a certain altitude. So I would like to recommend you to do this CanSat. Okay, so it's almost time. So this is what our history. So we started from one new CubeSat, and we have been developing a little more sophisticated satellite gradually. And not only keeping our technology, but also we transfer our technology to venture company so that they can make a business out of this technology. So we created several venture companies, as well as we are collaborating with several established venture company. And once they can make a business and they get something like a private fund, and then the money, part of the money will come back to the university. Then using that money, we can do the next phase, research and development. So it's a kind of ecosystem. Ecosystem is very important between the university and the company, because governmental money is very much time limited, maybe 3 years or 4 years. After that, how we can keep our employees in our universities. So if we have this kind of ecosystem together with a company, then we can continuously keep the money, and we can keep the employees and the technological development as well. So this kind of ecosystem is very important. And the one ecosystem is, going on together with Aerospace. As I said before, my student, Dr. Nakamura, is now the CEO of this, university company, and they are now targeting to obtain the 15 satellite constellation with a 2.5 meter resolution. It is called Axel Globe concept. They already launched 5 satellites, and they can obtain this kind of the 2.5 meter image every 3 days. So if they become the 15 satellite constellations, they can do that every day. So this is their concept. Another company is called the Synspective, which focusing on the synthetic aperture radar, data observation. And then we have been developing the bus system, satellite bus system for this company, and they already launched three satellites. And another one is 6U CubeSat. The company named Aerospace has been established, and so 8 PhD students in my laboratory started this company, and now they are focusing on the development of the 6U CubeSat. That is a very, very affordable satellite size, and it has a very high level attitude control capability, and we expected to utilize it for the various missions like Earth observation, space science exploration, capacity building, and so on. So this is another company. And in this way, in Japan and many startups occurs. I think in space, maybe we have about 100 startups in the space. So the red part is a company which we collaborate with. So we are collaborating with many companies like this. So it a little past the time limitation, but I'd like to show you finally. This is a very important concept. So this is show the importance of the failures and the iteration. The improvement can be written like this: 1 plus A times N. A means improvement at one time, like a one launch or one demonstration, and the N means how many launch, how many demonstrations occurs. And up till now, we cannot make N larger, like once per 2 years or something like that. So in order to make an improvement, we want to make A larger. That is very difficult because at one demonstration, we should make a higher level satellite at once. That is very difficult. You should make a very complicated system. You should make some redundant system, and you should do a lot of experiment, ground tests, and so on. So making A larger is very important. In the result, if we want to make A larger, then the result is that N gets lower. So that is a current or space development up till now. But the SpaceX are doing a very, very different thing. A is very small, like 0.01 or 0.001 or so. But N is very large. They are quickly, launch and failed, launch, failed, and so on. And it's very large. So as a result, the development speed is very fast in the last. So this is the current concept of the space development. So it's very difficult to do this, make it larger. But we should make this kind of something like a concept of the satellite development. So that will make your development start speed up. So it is very difficult, but please consider and try to realize that how you can make n larger. Okay, do fail and then a feedback and try again. So that kind of a thing is very, very important. Okay, and the final one is also very important. If things are not failing, you are not innovative enough, innovating enough. That is a concept. That is a words from Elon Musk. I think that what is also very important. Okay, so this is a current concept of the space development in the world. Okay, that's all from myself, and please enjoy the follow-on presentation. Thank you very much.
Thanks. Thank you, Professor Nakasuka, for the enlightening and informative lecture. As Professor Nakasuka mentioned, CanSat and the CubeSat were the first step in the Japanese University Practical Space Engineering project. Professor Tsuda is a professor of astronautics at the Japan Aerospace Exploration Agency and the project manager of the first CubeSat of Tokyo University, and also a project manager of Hayabusa 2 asteroid sample return mission. Professor Tsuda was the first generation of CanSat student. Let's listen about an experience of the first generation of CanSat student. Please welcome to the platform Professor Tsuda.
Okay, thank you very much for the introduction and good morning. So first of all, congratulations on the, I think, 20 years anniversary of UNISEC and also the 10 years of anniversary of the UNISEC-Global. So I am one of the first, as in the title, I am one of the first generation CanSat guys. And as Kawashima-san said, pointed out in the opening remarks, 20 years ago, I didn't believe we can make the satellite by ourselves. But and I was one who was in the center of the turning point from impossible to possible. So at that time, I did not think we will change the space engineering world. We did it just because it is fun. But at the same time, we felt we may change something. So and the result is what you see now. So my contribution is just a small one, but I thought it would be meaningful to share my experience just as an example of the effect of the CanSat and the CubeSat educations. So as in the title, I am the first generation CanSat and CubeSat guy, and my career began with CanSat. So I am so grateful that I can present an example of the space engineering career, what can happen as a result of the CanSat program to today's participants. So let me first briefly introduce myself. My name is Yuichi Tsuda, and currently I am a professor in ISAS JAXA. ISAS is a Japanese Institute for Space Science, and my research field is in spacecraft system, solar system exploration, and astrodynamics. And my experience started from, let me use the laser pointer. Yes. My experience started from CanSat, and then CubeSat development as a student. And after that, I joined ISAS as an assistant professor, and then participated in the Icarus and Hayabusa 2. And for the CubeSat, I was the student project manager. And Icaros, deputy project manager, and HEPSA 2, I was initially the project engineer who is responsible for the spacecraft design, and then became the project manager of after the launch of HEPSA 2. So let me start from the beginning of my experience. The story started in 1998 when I was a student in Professor Nakasuka's lab, and he already gave a talk. And one day, professor and I and some other students had a lunch in the university cafeteria. When he asked us, there will be a workshop in Hawaii. Do you want to go? My answer is, well, Hawaii, why not? By the way, what will we do there? So actually, even professor, professor did not exactly know what would happen in the workshop. And the name of the workshop was University Space Symposium, as Professor Nakasuka told. And this is the place the story began. And in a sense, charm of Hawaii was the primary contributor to the beginning of the CanSat program. And so my first lesson learned is luck is important. And I traveled to Oahu Island of Hawaii with Nakasuka sensei and a few other students in my lab in the summer of 1998. And there we met Professor Bob Twiggs of Stanford University at that time. And I'm so honored to have him in this conference in the first presentation. And in that workshop, he passionately proposed like this: let's make a satellite out of the Coke can. And we didn't understand what he said. So we could not believe satellite can be made from a juice can. And on top of that, we could not believe we, just a student or just a small lab, can make a real satellite and launch it to space. But it sounded super exciting, and the way the Professor Twiggs talked sounded real and practical. So after doing small internal lab meeting in Hawaii, then we decided to take part in his proposal, and we did not know the way, but we were excited a lot from that idea. And the first concept that he proposed was like this, as the Nakasuka sensei already showed. And launching the Coke cans developed by several teams are launched together and deployed in space, and then operate at all of them at once in the next USS meeting 1999, 1 year later from the original USSS. The research field of our lab was the space engineering, so we already knew something about the space engineering by textbooks, but we knew little about how to use our hands to make something for satellites. And the first thing we did was to go to Akihabara, which is a city with a full of electrical shops in Japan, and bought CPUs, condensers, resistors, and at the electronic shops, and made printed circuit board by photoresist by ourselves, and so on. And another thing we did was to buy as many juice as possible for structural design and experiments. And you can see very, very primitive handmade circuit board with bad soldering. But anyway, we started making a CanSat. And in the meantime, the Professor Twiggs realized that it was difficult to launch the satellite into space and in just 1 year. So, and proposed an alternative option by collaborating with amateur rocket people based in Black Rock Desert, Nevada in US. And let's do the suborbital experiment. That was his new proposal. And finally, we completed the fabrication of the first CanSats. We made 3 CanSats. CanSat number 1 was to do the attitude control and power generation experiment. And number 2 is to measure the high altitude temperature and pressure and some flight environment data. And the number 3 is to transmit the real-time movie from the high altitude. So and I was leading the second CanSat, CanSat number 2, the sensor CanSats. And in the summer of 1999, we brought three CubeSats that we made to Black Rock Desert, and everything was new to us. And actually, everything was new to everyone because this was the first CanSat even. And our CanSat was loaded to a rocket provided by the medical doctor, and it was a very beautiful rocket. And the launch was successful, and 2 CanSats were success, but only the second one, my CanSat, failed. And after the separation from the rocket, the parachute was deployed successfully, but I could not receive any signal from my CanSat. The reason was very simple. I changed a transmit antenna just before the launch because it better fit to the rocket. And I thought it had better performance. But in reality, we only tested with the old antenna before coming to the desert. So I learned a very important lessons learned from this. Test as you fly, fly as you test. So I think all of you already know about this. So this is an essential rule for the space engineering. But for me, I learned this through very bad experience. Unfortunately, I put the memory in my CanSat, and all the flight data could be retrieved after we retrieved the CanSat from the desert. So another lessons learned for me was prepare backup. And we continued CanSat activities after the first Black Rock event, but at the same time, we strongly felt we want to make a real satellite. And in the next year, various workshop again in Hawaii, the Professor Twiggs proposed a different idea. Let's make a 10 centimeter cubic satellite. So we thought this is a great idea because through the 1 year experience of developing CanSat, we found it very difficult to accommodate many functions to cylindrical can. And IC chips are all square shapes, and it's easier to make square PCBs than rather round circle PCB. So we started to plan what mission we have to do, or we will do, with a CubeSat. And at the same time, we were interested in ultralight structure application in space as a lab research activity. And this is one of the such example that I made, the Pluto Explorer concept. This is one of this is equipped with a 200-meter diameter huge membrane, very lightweight, thin membrane, attached with the solar cells so that the spacecraft can be driven merely with the solar power in the Pluto distance. And we thought to apply this concept to the CubeSat like this. So after studying the feasibility again and again, and finally the design resulted in CubeSat without membrane, like this. We realized that we have to begin with the very, very basic to obtain fundamental know-how of the satellite fabrication. So we decided to keep it simple, stupid. So, and after we succeeded, then we will be able to think about more sophisticated space application like space membrane. So the first CubeSat only equipped with the camera is here to take the picture of the Earth. So these pictures are like showing the interesting and very challenging part of the pioneering work. We do everything by ourselves, building up a clean room, asking professionals, and many primitive and maybe somewhat stupid experiments to proceed forward to make the actual satellites. And then in 2002, we completed the world's first CubeSat named Psi. Psi stands for X Factor Investigator. And you can see camera here or here, and behind it you see a power board, COM board, and so on. And finally, we could make this kind of very beautiful CubeSat. So comparing to this, you can see our growth. And our CubeSat was launched by a Russian rocket from Plesetsk, and launch was successful. And I cannot forget the moment the first signal was received. in our ground station. So it was a beautiful Morse code, as Professor Nakasuka already showed us. And after that, CubeSat sent us a beautiful Earth scenery regularly. And surprisingly, the CubeSat is still alive. It's alive for 20 years. And in orbit, still sending Earth images to us, becoming a little bit yellow and yellow. And one of the things I'm really proud of is that our CubeSat lives longer than most of JAXA and NASA satellites. Then from 2003, I joined ISAS, the Space Science Institute of Japan. And there I continued my research on membrane. So one regret during my student life was I could not realize the space membrane. So I did several conceptual study on it, Pluto Explorer, CanSat membrane experiment, and the CubeSat membrane experiment, but all finished at the conceptual study level. But in ISAS, there was a study group on solar cell, which wanted my idea of the space membrane technology. And 3 years later, finally I made it. So after we did several experiments, we proposed an interplanetary solar cell mission in 2007 to JAXA and was authorized to launch in 2010. It's a 300 kilogram small spacecraft, and you can see a membrane here, which is the solar cell surrounding around the spacecraft body, and which is based on our idea when I was I was a student. And the Icarus was launched on May 21st, 2010, and flew to Venus. This is so this is the mission sequence of the Icarus, and we actually confirmed that the spacecraft was propelled by the solar radiation pressure through the very large membrane, and the Icarus made a Venus flyby 6 months later, and extensive in-orbit solar cell experiments were conducted in this 6 months, and some extended mission after then. So this Icarus did a selfie to confirm the cell deployment in interplanetary field. I think this is a very rare case that spacecraft go to space to get a picture of itself. And for this, we made a deployable camera called DCAM, which is shown here. You can see it looks like a can. And it was developed by one of my colleagues, another first generation CanSat guys. So this is actually a descendant of the CanSat. And I think this is the first example that the CanSat was applied to interplanetary mission. And the result was so successful at taking such a beautiful selfie of the solar cell craft taken from a really nice distance in the interplanetary field. And as I led the Icarus mission as a deputy project manager, my interest was directed even more strongly toward deep space exploration. And I was lucky enough to join the Hayabusa 2 project from its beginning. You may know it successfully completed the round-trip mission to the asteroid Ryugu and back to Earth in 2020. And let me use the rest of my presentation time to introduce the Hayabusa 2 achievements. And this is the entire mission history of Hayabusa 2. It was launched in 2014, arrived at the asteroid Ryugu in 2018, and stayed there for around 1.5 years, doing many challenging operations such as rover landings, spacecraft landings, and sample collection, kinetic impact, and so on. And after that, Hayabusa 2 returned to Earth in 2020. So these were done all in success. And now, because the time is limited today, I would like to show a 30-second movie to cover the Hayabusa 2's 6-year flight. 30 seconds is very short. I hope you can catch up with me. So anyway, this is the 6-year mission, all in success. And the asteroid Ryugu, which is unexplored before by human, is really surprising, and many discoveries are there. It's a top-shaped asteroid, and the size is about 1 kilometer. And the biggest headache for us was that the surface of Ryugu was very bumpy, covered with full of boulders and craters. That imposed us very difficult challenge to land on the asteroid to get the sample from there. And let me just show you the summarized accomplishments of Hayabusa 2 around Ryugu. And first, we deployed as many as 4 mobile rovers to the surface of Ryugu. And we did a simultaneous operation of 3 rovers, all of which moved and hopped around Ryugu surface successfully and sent back to us the precious close-up observation data via the main spacecraft. And we succeeded in 2 spacecraft landings for sample collection from 2 different sites. The first one was in February 2019, and the second one was the July 2019. And because of its far distance, 300 million kilometers away from the Earth, everything has to be autonomous, and we achieved about 1 meter or less accuracy, landing accuracy on that far distant asteroid. And we also succeeded in a kinetic impact operation. We could generate a huge artificial crater, 18 meters in diameter, 3 meters in depth. By this operation and the full set of observations of the target terrain before and after the impact, as well as a process of the crater forming were all obtained. And then the second landing aimed just 20-meter distance from the crater center so that we could collect the subsurface material exposed by the artificial kinetic impact, so which was also successful. And the last thing we did was 3 small objects orbiting around Ryugu to contribute to the gravity science. And the Hayabusa 2 spacecraft system looks like this. It's a 600-kilogram spacecraft equipped with a solar electrical propulsion system to make a round-trip interplanetary cruise, and the several instruments for asteroid proximity operations. So it's a really complex spacecraft, and just a 1.5 meter cubic structure. And in the development phase, I was leading the engineering part of this spacecraft, and it was really a puzzle. So how to pack as many as 14 scientific instruments and ion engine and the spacecraft computers into just around 1.5 meter cubic structure. So as Professor Nakasuka analyzed, we Japanese may be good at making this kind of dense spacecraft because we live in small houses. So one of the outstanding features of Hayabusa 2 is that it brought as many as 12 deployables to space. Rovers, landers, and kinetic impactors, and artificial navigation landmarks, and so on. And most of them were separated around Ryugu, except for, of course, the sample return capsule, which was separated toward Earth. And although these are not direct descendants of CanSat nor CubeSat, you can easily imagine how challenging it should be to put on these kind of small robots on a flagship class mission or national mission. So these are there are a lot of engineers within the Hayabusa 2 team who experiences CanSat and CubeSat, and who understand intuition behind the nano-satellites, and thanks to their CanSat and CubeSat experiences. So that made this kind of many robots aboard mission possible. So let me show you some of the highlights movie of the asteroid proximity operation. So this is the movie of the touching down to collect the sample. And it is actually a touch and go sequence. The spacecraft landed to the asteroid for about 3 seconds and then shoot the projectile and collect the fragments as a reaction of the projectile shooting and transported that to the root of the sample horn and store in the reentry capsule. So these sequences are all successful. And just 1 month after the success of the first touchdown, we attempted another ambitious mission, the kinetic impact. A device just separated from the spacecraft was called Small Carrier Impactor, or SCI. And this guy will soon explode. And before that, HEPS-2 has to escape to the backside of the Ryugu to avoid the damage by the explosion. And then, after that, the SCI detonates like this and make an artificial crater. And this system can be accelerated to a 2 kilogram pure copper bullet to 2 kilometers per second at once. And as the spacecraft had to escape, it cannot observe the impact process. That's a pity. So on the way of escaping, HEPS-2 was to deploy a remote camera called DCAM-3. You can see it looks like a CanSat, another CanSat. It's a single-use disposable camera only to shoot the cratering process, and before damaged by the impact fragments, this DCAM-3 transmits the image data to the mother spacecraft. And it was really an acrobatic operation, and it's also appropriate to use the CanSat-based technology for this kind of very acrobatic and challenging operation. And we succeeded in getting this kind of very beautiful movies of the crater forming. The impact ejector could be observed for more than 5 minutes. So it was actually very, very slow process and very, very big process. The fragments went up to about 40-meter altitude. And the spacecraft could go back to a vicinity of Ryugu after this impact operation and observe the terrain and compare the terrain before and after the impact. That's very important for the science. And we could confirm that we could make the 18-meter diameter as the crater, artificial crater on the surface of the Ryugu. And then we attempted the second landing to a vicinity of the artificial crater we made to get the subsurface material. This is the onboard camera-based movie at the final moment of the second landing. And by this success, we marked the world's first multiple landing by one spacecraft and world's first subsurface material collection beyond the moon. And the landing accuracy as good as 60 centimeter to the celestial body 300 million kilometers away from the Earth. So they were all too satisfactory to the mission. So after 1 year of the return cruise, HEPS-2 came back to the Earth. And then the reentry capsule was separated from the mother spacecraft and then landed to the Umera Desert, Australia, South Australia. And they landed reentry capsule with a parachute can be seen here. And then we've got a sample of Ryugu after opening the reentry capsule. So our mission requirement of the sample amount was 0.1 gram. But we actually obtained 5.4 gram. So more than 50 times larger than we expect. And this 5.4 gram is the total amount from the first and the second landing. So you can see very black debris and sand, which was what we had expected for more than 10 years. And water is there, carbon is there, and as we expected, and many wonderful scientific discoveries are there. So now we are delivering samples to researchers all over the world. And so now the worldwide academia are tackling with these fascinating extraterrestrial materials. And on the other hand, HEPS-2 spacecraft itself is still flying. At the Earth's return, we separated the spacecraft separated the reentry capsule, and the spacecraft side still continues its flight again toward the interplanetary field. And we confirmed that almost half of the fuel is still remaining. And the spacecraft is healthy, so we decided to make the spacecraft head to 2 new asteroids. these asteroids are scientifically very interesting in a different way from Ryugu and have not been visited by human yet. So we call the extended mission Hayabusa 2 Sharp. Just like the music sign, we aim for the challenge of a semitone up. And as a space engineer, my voyage is still going on. And I am now in a new proposal team for the next generation solar system exploration mission in Japan. And I don't know this will become real, but challenging to unknown, challenging together are what I learned from the CanSat and the CubeSat. And my attitude toward the space mission is not changed from then. Okay, this is the final slide. To me, the CanSat was the first step to my career. I've got many lifelong friends in CanSat and CubeSat activities, and some of them played a critical role in the mission like Hayabusa 2 project with me for in this photo. By the way, this photo was taken in the control room when we succeeded in the historical landing of the Hayabusa 2 to the asteroid. And so I really appreciate CanSat and the CubeSat. I also thank Professor Twiggs, and also thank Hawaii. They gave us many good friends, wonderful experience, and essential skills. And I hope the world of small sats more and more contribute to the space missions, more to the outer space, beyond the moon, and ultimately beyond the solar system. And as Professor Twiggs said in the opening remarks, recalling the original concept of CanSat or CubeSat, the simplicity is important to stimulate education and stimulate young people. I agree with that. And at the same time, as a player of space engineering, we want to make something new, something innovative. So how to combine how can I say, innovativeness and simplicity, that might be a key for the small sats community to grow more. So that's it, and thank you for your attention. Thank you very much.
Thank you, Professor Tsuda, for the very enlightening and stimulating experience. I hope that all of us will make use of it. Thank you very much. So it's a time now. I think we have the lunch break. Then, please. Yeah, go ahead.
Okay. Announcement, very important. We will move to the different building for mission idea contest. So mission idea contest presenters, please go with EOS. Remember this face, okay? And you guys need to leave here at 12:30 because you need to